Okay, today we're going to start with chapter 3, talking about extrema. Now, extrema is maximum or minimums, okay? They're extreme values. When you're talking about the max or min value, it is talking about the y value, okay? You always want to remember that. The first thing, there's a theorem. If f is continuous on, now this right here is a closed interval, okay? On the closed interval from a to b, then f has a maximum and a minimum. Okay, so this is a closed interval, this first one, example f. F of x is defined on 1, 7. The max is right here, so the max is 10, and it occurs at x equals 1. Okay, the min is right here, that is 2, and it occurs at x equals 7. Okay, now over to the right, that is not a closed interval. Okay, that's defined on the open interval from a to b. Actually, you can see from, what is that, 1 to 6. It's defined on 1 to 6. So the max is right up here. That is a max of 7. Okay, and it occurs at x equals, that is what, x equals 3. And the minimum, there is no min. Okay, the minimum is non-existent. Now, the reason it's non-existent is because here and here are both open, which means it doesn't reach that value. It reaches infinitely close to that value, but not that value itself. Okay, so next we are going to go to the next page. Give me a second. Okay, this one right here. We have if f of x is a max on an open interval containing c, then f of c is a relative or local max. If it's a min, then it's a relative or local min. Relative extrema happen only at critical numbers. Now, we have to define critical numbers. Critical numbers are where f prime of x equals 0 or does not exist. Okay, f prime of x equals 0 or it does not exist. So, what happens when f prime of x equals 0? This we know from the last chapter. When f prime of x equals 0, we have a horizontal tangent. Okay, horizontal tangent line. So, to this graph right here, we have horizontal tangents right here and right here. Those are critical numbers, okay? Those are places where f prime of x equals 0. We're going to have critical numbers there, which means it's going to, or it could be, a relative or local extrema. Now, what that means, it's not an absolute. Absolute was like back in the first example where you have an absolute max and absolute min on a closed interval. You don't always have absolute because, especially in this case right here, this graph continues going up infinitely. This continues going down infinitely. But right in this area, we have what's called a local or a relative max. And right here, we have a relative or local min. Okay, so h of x has a relative max of, what is that, 2, 4, 6, 8, of 9, and it occurs at x equals -1, and there's a relative local min down here at -2, and it occurs at x equals 3. H has 2 critical numbers. Okay, there are 2 critical numbers there, 2 places where f prime of x equals 0. All right, next page, we have the definition of critical numbers. Okay, so critical numbers, I already went over this, but f prime of x equals 0 or does not exist. Okay, now the theorem says at x equals c, there's a local max or min. If there's a local max or min, then c is a critical number. Okay, and remember, it's where f prime of x equals 0 or does not exist. So let's look at an example of that. All right, the following function is defined on all reals. Find the critical values of this function. Okay, critical values where f prime of x equals 0, which is here, here, those 2 places it equals 0, or it does not exist, which is here and here. Okay, it does not exist because those are sharp points or cusps. All right, so our critical numbers are at A, x equals A, B, C, and D. At each critical value, identify whether it is a local or absolute extrema and discuss the value of the derivative. All right, so this graph continues to go up here, which means we're not going to have a max, an absolute max. This graph looks like it's leveling out here and is going to have an asymptote there, okay? Which means we could have an absolute min down here. All right, so, but let's look at x equals A. So, A is a local min, okay? Right in this local area, A is a minimum. B, right there is a local max, or relative, whatever word you want to use. Right in that local area, there's a max at B. C, we're going to call x equals C an absolute min. Also a local min or a relative min, but that's our absolute because this one keeps going up and this one is leveling out to an asymptote. So C is going to be your absolute minimum there, okay? And then at x equals D, we have a local max, okay? Because right in this local area, there's a maximum there, okay? So next, we're going to look at finding critical values. All right, so we said critical values occur when f prime of x equals 0 or does not exist, okay? This is a polynomial. There's not going to be a place where f prime does not exist, okay? That would be, you know, when you have a fraction, a denominator where the value could be 0. But one like this, all we're going to do is find the derivative. So derivative 3x squared plus 6x minus 9, and we're going to set that equal to 0. And so factor out 3. And then we factor, that's going to be what? X plus 3x minus 1. So we have critical values at -3 and +1. And it's as simple as that to find your critical values. Okay? So next, sorry, it takes me a minute to change page on here. All right, find all absolute extrema on the interval from -1 to 2. Okay, you might think, where do I even start? Well, first we have to find our critical values, because you know if you have a critical value, there's going to be a local max or min there, or an absolute. Actually, okay, absolute extrema, and it's a closed interval. So let me show you how to do that. So first of all, find your critical values. So we need to find f prime of x. That's 12x to the third minus 12x squared, and we need to set that equal to 0. Factor out 12x squared, you're left with x minus 1. So we have critical values at 0 and 1. When you are looking for absolute extrema, you need to test your endpoints, okay? Back in example 1, we had our endpoints could have been our max or our min, okay, if it's a closed interval. So we need to check the endpoints and the critical values. We have the endpoints, and then also put in there the critical values. And then plug them in. F of -1, if we plug in -1, that's 3. That's going to be 3 plus 4, which is 7. If we plug in 0, 0 minus 0. If we plug in 1, 3 minus 4 is -1. And if we plug in 2, we have, let's see, 2 to the 4th is 16 times 3 is 48 minus 2 to the 3rd is 8 times 4 is 32. So that is 16. Okay, so you can see from here, -1 is our absolute min, and 16 is our absolute max. Okay, so when you have a closed interval, you need to test the critical values and the endpoints. Okay, always easiest to set up a table there. All right, next example. We have use a calculator to find all extrema on the interval from -6 to 4. Basically, when you're doing this, okay, put this interval, whoops, don't move that whole thing. Put this interval into your calculator. graph it, and then find your max and min. On the 83, 84s, it's going to be second trace, and you'll see a maximum and a minimum. I believe you learned how to do this last year in Honors Pre-Calc. If you don't, we can talk about it more tomorrow. But I don't have the calculator up on the screen to show you. But I believe it's second trace, and then there's a max min. You got to do left bound, right bound, and in the middle. On the inspires, there's a function there. Just hit menu on your graph, analyze graph, and it should be under max and min there. Okay. Okay, so the last example, find the value of a so that that function has a local extreme value at x equals 1. Okay, well, we know local extreme values occur at critical points, and a critical point is when the derivative equals 0. So let's find the derivative. F prime of x that's going to be 2ax plus 14. You want to set that equal to 0. So let's see, 2ax equals negative 14, divide by 2, and divide by a. So it occurs at negative 7 over a. So when x equals 1, so you know the extreme value occurs at x equals 1, so 1 equals negative 7 over a, so you get a equals negative 7. When a equals negative 7, that function would have a critical value at x equals 1, which means there's a local extreme value, okay, either a max or a min, and you don't know that unless you plug in other values to find it. All right, so that's it for your examples. Go ahead and try the practice that's in your packet as well as the homework for class 1, and we will discuss it all tomorrow.